You all are in campus now, right? Because your NSEM is offline, right? Okay, so just cross check if it is recording or not. It is recording. Screen is shared, only one online. Okay, so from this week we'll discuss chapter 6, that is parallel processor from client to cloud. But before starting this chapter, we need to clear some basics, and those basics I could not able to cover in much detail in this course, but these basics are very important. Why? Because if in future if you want to take some advanced level course of computer architecture, then there are some basics very important, and at least you should know the terms. That's why I'll not start chapter 6 today. I'll cover chapter 6 tomorrow as much as I can cover. And after that, if required, then I'll upload a recorded lecture. And next week there will be three lectures on securities, but out of these three lectures only one lecture will be included in your syllabus, that the lecture that I will take. But two lectures will be taken by PhD scholars. I'll request you to attend this, because you will understand what are the security issues are going on. One lecture will be on ransomware attack on SSD memories, and another uh, talk will be on what are the different security issues on last level cache. So these two lecture I'll not include in course, but not include in exam only. You can consider it in course, but not in exam. Why? Because you must have also be busy in your project work also. So I'll not give this load. So maybe you will complete your project. And what is your submission date of project? Huh? 30. And when your NSM is completing? 9th April, 9th May, and grade submission date is 18th, right? Then maybe I'll extend. I'll give you 2 3 days after NSEM if you need, because I cannot check it during NSEM. And if you want that after NSEM, if you want to work 2 3 days, then it is fine, because I'll check it on 12 or 13. So maybe I'll extend it. If your NSEM is finishing on 9th, then maybe 10, 11, 12 you can work. Maybe I'll give you 13, but in that case, in 14th your evaluation will be there on 14th or 15th, because I have to submit everything, grades and all, by 18th. Okay. Huh? No report, only the code. This project evaluation will be done by me only, not TAs. So I'll check the code, how much you have done. And there will be a viva, and based on that I'll give the marks. But before that, you have to submit the code, and my TAs will check if you have copied or not. That is important. वो नहीं छोड़ेंगे, नहीं तो सीधा सीधा कॉपी करते हो. हाँ. वो क्लास टेस्ट में भी सारा आंसर सेम कैसे होता है? हाँ. आई डोंट केयर, और मुझे कुछ लेना देना नहीं है उससे, क्योंकि अगर 100 में से 20 बच्चे सीख रहे हैं, मेरे लिए काफी है. लेकिन से फिर भी क्वेश्चन सेम तो नहीं होना चाहिए. वो 0.89 वाला जो आंसर है, वो भी सबके सेम हो जाते हैं क्या? दैट टू इट इज रॉन्ग, आई थिंक, राइट? सबके रॉन्ग कैसे हो रहा है, वो भी 1 मार्क? व्हाट्सएप ग्रुप में कौन शेयर करता है? हाँ? ऐसा तो मत करो. एंड योर एंड सेम इज नाउ ऑफलाइन, उसमें क्या करोगे आप? सी देयर इज नो वे. मुझे पता है कि इसको बंद करने का कोई उपाय नहीं है, इसलिए मैं ज्यादा एफर्ट भी नहीं दे रहा हूँ. हो सकता है बाकी फैकल्टीज देते हैं, मैं कोई एफर्ट नहीं देता हूँ कि मिड सेम में या क्विज में कौन कॉपी किया कौन नहीं किया. आई डोंट केयर, कि देयर इज नो वे टू 100% प्रूफ. कोई वे नहीं है जिससे मैं बोलूँ कि इफ वी फॉलो दिस देन इट विल बी प्रिवेंटेड. देयर इज नथिंग लाइक दिस. और बहुत ज्यादा करेंगे तो आप लोग बोलोगे क्या प्रूफ है कि मैंने कॉपी किया है, राइट? सो कौन जाएगा इसमें? बट इन असाइनमेंट आई हैव प्रूफ. वहाँ पे चेक हो रहा है कि मल्टीपल पीपल सबमिट द सेम कोड. So that's why till whenever it is from 2000, I think 2020, the moment it is started online mode, my intention is I'll teach for those who want to learn this course. And for evaluation, it I know that evaluation is not possible. 100% correct evaluation is not possible in online mode. At least जो facility हमारे पास है उससे तो नहीं. Okay, but the end sem will create a difference because all are now offline. Okay, so let us skip this chapter 6 for today, and I'll use a slide, but I don't think I'll not share this slide because there are only 2 3 slides are here. So since I'm recording the lecture, so recorded lecture will be enough. I'll not upload this. So these slides are not well prepared because I'll not share. I'll only explaining. I've only designed it to save time in class. So one very important point that I missed is virtual memory. And honestly, if I want to take this concept virtual memory in class, then 2 weeks is required to complete 1 or 2 weeks because it's a very huge area. And all CSE, I think CSE student will understand it much in better detail in operating system course. I'm not sure about other branch, but CSE people you will learn virtual memory in operating system course. But this concept is very important, so at least you should know what is virtual memory. Without the concept of virtual memory, some point maybe it will be difficult for you to understand in chapter 6 also. So to understand virtual memory, we'll start with a term called program address space. Program address space means we write a C program, and after writing the C program, it will suppose it is converting to a RISC B program, or suppose you are directly writing a RISC B program. So when we write a RISC B program, we assign some addresses like load. It is going some address, jump. It is going. We give some address. So what are those address, and what is the maximum capacity of those address? So if it is a 32-bit machine, then we can assume those the capacity is 4 GB. Okay, so program address space is 4 GB. So whenever you are writing a RISC V program, you can assume that my address space is 4 GB. So so whatever so if there is a 4 GB memory, so byte address, suppose it is starting from 0, so 0 to 4 GB, any address you can use, you can assume this. So if you assume this, so your program address for one program, your address space is 4 GB. And suppose assume that in your desktop the RAM is of only 1 GB. If you have only 1 GB RAM and the program address space is 4 GB, and then how you'll map? Suppose the first address is mapping here, second address is mapping here, third address is mapping here, fourth address is mapping here. What about the other addresses? For this address there is no corresponding main memory, isn't it? Main memory means RAM. So suppose I assume that this address is suppose 2040. Suppose I'm assuming this address is 2040, and in your risk base is suppose there is a uh, unconditional jump instruction kya tha? JL, right? JAL. Suppose X120. Suppose maybe syntax is not correct. If you write this type of line 2040, suppose, then there is no corresponding entry in main memory. So your program should crash, right? But that is not happening, right? If your desktop has two RAM or four RAM inserted, if you remove one RAM and restart your computer, then also your computer will work, right? So what is happening inside, how it is working? And if you have multiple program instead of one program, if you run 2 3 programs at a time, then each program will assume that they have 4 GB of space. And then how this 1 GB of RAM is handling all this program address space. So that's why we use virtual memory. Virtual memory is a it's assumes a memory which is not actual memory, it's a virtual memory. But before that, we have to understand one more point. It is called page. So we know a concept called block, right? So block is the minimum or the unit that we fetch from main memory to cache, right? If there is a miss in cache, we go to main memory, fetch a block. This is the unit that we fetch, right? But in main memory, it is called page. So if there is a miss in main memory, when we go to HDD, hard disk, or we can call secondary disk, then the minimum amount, the minimum content that we fetch is called page, one page at a time. So you will know more about page in operating system course. So that this, if you remember these two terms, then only then it is enough here. That block is a term is valid for cache memory only, and when you go to main memory, the minimum content is called page. And if there is a miss in main memory, when you go to secondary memory, we fetch a page. complete page. And if you remember the DRAM that I said, in normally in one row we store one page. Okay, so here you can assume that each entry here that I've shown here, you can consider this as a page. So first page is mapping to first of RAM, second is mapping here, third is here, fourth is here, what about fifth? It's not possible to map. So in virtual memory, what we say that no, this 4 GB of this the program address space is available in HDD. It's not available in main memory. Okay, the 4 GB space is there. Each program has 4 GB of space, but that will be available in HDD, and there will be there will be a mapping module here. Okay, so if this address page wants to store something in main memory, first it will go here, and this mapping module will redirect it to here somewhere. Okay, then maybe this one. Uh, I'll just write a line here for mapping module. Otherwise, there is a space issue. So suppose this mapping module is forwarding it here. Second is forwarded here. Third is forwarded here. Fourth forwarded here. Suppose ये फिर भी ऐसे ही कर देता हूँ मैं. I should have. I don't know how to change color. One is going to two. Suppose three is going to four. And I hope you're understanding. Somehow I'm not this. Some of I should change the color, but anyway. So this way you can map. So maybe in this map, maybe one row, one page of here is also mapping. So this remapping unit is very important. How? Suppose now this is full. Now this main memory is already, there are already 4 pages are there at this moment. Suppose you, if you want to fetch this page in main memory, then you will go to this remapping unit. This is normally called page table. You will go to page table and check what is the status of this page. Suppose number the page like 1 2 3 4 5 6 7 8 9 10 11, and assume that here the number of pages are 1 3 4 5. These pages are in main memory. Now I want to fetch page 8. Then what I will do, first I'll go to this page table, and I'll check if what is the, if 8 is already there or not. If 8 is not, if 8 is not in main memory, then I have to fetch 8. But where to fetch? This is already full. So the page table store this mapping that okay, row number 1 of this virtual memory is this is called virtual address, this is called physical address. Okay, row number 1 from virtual address is mapped to row number 1 in physical address. Row number 2 mapped to row number, suppose 3. So 2 2 3 3, suppose like this. Row number 4 is mapped in 4, suppose like this. So in that case, if I want to sorry, not 1 3, right? So 3 2 is not here. uh, Blackboard होने से अच्छा होता. Just 1 minute. I don't want to confuse you. Physical at page 1 is virtual page 1 is mapping to physical page 1. Virtual page 3 is mapping to physical page 3, physical page 2. Virtual page 4 is mapping to physical page 3, and virtual page 5 is mapping to physical page 4, right? This is how what I have written. Now I want to place virtual page 8 in the main memory, so I don't have any space, so I have to apply a replacement policy here. So suppose if I apply LRU, then maybe the first one will replace. So I'll replace this, and in place of this, I'll place 8 now. So now virtual page 8 is now will be stored in physical page number 1. So this is called page table. So the purpose of page table is to translate or convert the virtual address into physical address. Okay, so maybe you have a very large number of virtual address, and you have only limited number of main memory physical address, but it is not required that all the pages will be in main memory at a time. Other pages at this moment, okay, this is 8 9. So at this moment only 8 3 4 and 5 are in main memory, right? Other pages are in HDD. So this virtual memory is actually, when we say memory, we normally only say about main memory, not the HDD. But because in entire course I never say anything about HDD, right? Secondary memory. So it is a memory. We assume it that okay, this is the entire memory available, but actually the memory available here in HDD. But when we write a program in assembly language, we assume that okay, the entire memory is available for me. I'll never think about that. Okay, only 4 GB is there, or only 1 GB RAM is there. What about I'm writing a program? What about if other person also write a program and two program will run simultaneously? I no need to think all this, because if I write another program, then another program will also have a virtual memory of 4 GB here, like this. A separate memory address will be there. That's why I have used a term called address space, if you remember. And I have uploaded a extra lecture on process, right? If you have watched that lecture, I have uploaded two lecture extra lecture on process. So in that lecture I have explained that what is called address space. So this is address space. If you run your first program, this is the address space. For second program, this is the address space. 4 GB address spaces are there. So if for and this address space in main memory is very very limited, and that's why the page table is responsible for converting all the virtual address to the physical addresses. But this page table is also actually very huge. So if I go to next uh, diagram here, this is actually your processor. So this is core, this is L1, suppose this is L2. Okay, this is main memory, and this is suppose HDD or secondary memory. It may be SSD also. Okay, so page table normally stored in main memory. Suppose here your page table will be there. So every time if when core request for a block, core will request for virtual address, right? Because you are writing a program assuming that 4 GB address space is there for you. So you for core will and your program is running on core. So every time core when core requests for a word, the address of that word is actually a virtual address. It's not a physical address. So when the core will request for a word, there should be someone here in between L1 and this core which will translate this virtual address to physical address. But the entire page table you cannot place here in chip, because page table is very huge. So a part of this page table will be here, that is called TLE or TLB. I think TLB. It is called TLB. Very small part. Okay, very small part of page table will be available in TLB. And every time when a request, the core will request for a word, that word address will be checked in this TLB, and the corresponding physical address will be forwarded to the L1. Okay, and if the entry is not in TLB, then it will go to page table, and then that part will be fetched from page table to TLB. So most of the time it will be hit in TLB. If there is a miss in TLB, then it is a time consuming process, because you don't have information of this translation, right? Then you have to go to page table and have to fetch the remaining information from page table. So I'm not going in more detail, but this is how it works. So if there is requesting for a code, then first you'll go to this TLB and assume that there is a hit in TLB. Then this TLB will say that okay, for this virtual address, the corresponding physical address is this, and then with that physical address, you'll start searching from L1. But there is a variation here also. The idea, the design that I'm saying here, L1 cache I'm assuming as physically indexed, but sometime it also possible that L1 is virtually indexed cache. In many times this type of designs are also exist, that L1 is virtually indexed, and after L1 from L2 physical indexing starts. So why this? Because in that case you no need to translate in L1. So if L1 is virtually indexed, then in L1 you can search with virtual address, but after L1 you have to see this TLB and have to find that if the now what is the corresponding physical address. So this is the main purpose of virtual memory. I am not explaining it in more detail, but if you see the memory chapter, that is chapter 5, there is a section for virtual memory. And in operating system you'll understand it in more detail, because I have missed many points, that how if there are multiple processes are running, right, multiple programs are running, then how they share the page table, how they have to share the main memory, what should be the replacement policies, These are, there are many concepts are there. So if you are running two process, suppose there are two core here, core 1 and core 2. So in this core, suppose process 1 is running, in this core process 2 is running. So I say they have separate address space, they have separate virtual address. In that case, if these two process want to share some variable, then it is difficult, right? They have no shared memory. So there are content you will understand in operating system codes, that how two process can communicate. Inter-process communication is also a concept, and there are you may need to write programs for inter-process communication also. If there are two process like this, P1 and P2, how they will communicate? Okay, so inter-process communication, how to use shared memory among two process. Suppose there is a memory here that can be shared by both P1 and P2, then that is called shared memory. So what is the concept of shared memory? I'm not going in all details, but suppose instead of process, I said about thread, right? So process, each process has their separate address space, but if it is thread, then this same process will have multiple threads like this, T1, T2, T3, T4, and all the threads will share the same address space. That's the main difference between process and thread. All the each and every process is their independent address space. But when you say about threads, no, it's not true. In case of thread, each all the threads share the common address space. Only things are different in threads are local variables. Local variables that will use are different, but other concept means main global variable, or if you allocate some memory with dynamic memory allocation, then this address space is same. And in C program, we allocate some a memory with dynamic memory allocation, right? So that memory allocation is part of the address space only. Suppose your program, you are writing a program called p1.c, and in that you have declared a array size of 500 using dynamic memory allocation. That memory will allocate, that is a virtual address only. That is actually a virtual address. So you can try, suppose if you are running your program in a 1 GB RAM or 1 GB in a machine where only 1 GB of RAM is there, you can try to reserve a virtual memory by dynamic memory allocation, that you can try to reserve a 2 GB memory. It will allow you. Why? Because of this virtual memory concept. Okay. If you want to know more about process and thread, then watch the two extra lectures I have uploaded, because if some that the two concept that have the two lecture that I have uploaded, that these two lectures are not on theory. I have explained everything by practically executing program. The moment you start executing a program, right, you know how to compile a C program. After compiling a C program, you will get an output file, right? If you don't mention any name, then default name is a.out, right? So when you execute a.out, immediately a process will be created, and a number of process number PID, that is called process ID, will be assigned, and you can check it dynamically, that the moment you press a.out, a process ID will be created. So so all these details I've explained in this lecture, and I think these concepts are not directly connected with computer architecture, but you must know, because without knowing the actual concept of process and thread, it will be difficult to understand parallel computing. Okay, some more concept. This is also a very big topic, instruction level parallelism. Normally we discuss it in advanced computer architecture course, but at least some basic concept you should know. So here this is called first concept is called superscalar processor. So in before midsem, in this class, we have understood the concept of processors, right? That if there is assembly language code, then first and there is a pipelining is there, then we'll fetch one instruction at a time, right? So suppose let me write a code here, add x1 x2 x3, and then maybe suppose or load x1 0 x5 sub x4 x3 x2 suppose. So in there are multiple instructions like this. So the concept that I've explained before midsem is one will the processor will fetch one instruction at a time. But in scalar processor, assume that you have multiple functional unit. Why it is fetching one instruction at a time? Because if I allow to fetch two instruction at a time, suppose if I allow that, in the same cycle you fetch both add and sub. So assume that there is no dependency. X1, X2, X3 maybe are 4, 7, 8. If I write 4, 7, 8, then there is no data dependency. Then also there will be a problem. There will be some structural hazard, right? Because if you are fetching two instruction at a time, then ultimately who will perform this addition? The arithmetic logic unit. But you have only one unit of arithmetic logic unit, and that one single unit of arithmetic logic unit needs to perform these two operation, add and subtraction, the same cycle. So there will be a structural hazard. So, but if you assume that you have two arithmetic logic unit instead of one, you have two arithmetic logic unit, then simultaneously you can perform two operations. So superscalar processor is based on this. Instead of one functional unit, maybe for addition, maybe for floating point addition, floating point division, you have multiple functional units, not just one. So in that case, you can fetch more number of instruction in a at a single cycle. So that concept is called superscalar processor. So normally this fetching one instruction at a time is very ideal. And modern computers can fetch multiple instruction at a time because they have different functional units. So whatever I'm discussing here, you just know the concept. If you know the concept, that will be enough. I'll whatever I'm explaining here, only this is included in the syllabus, because I'll not give you any more study material here, because normally we discuss all these things in advanced computer architecture. But at least you should know the term what is called superscalar processor. We in superscalar processor you can fetch multiple instruction at a time. Now the one more interesting thing I'll explain. This is called out of order execution. So for out of order execution, suppose you have a instruction add x1, x2, x3, then suppose sub x x x5, x2, x4, right? Then suppose here load x7, 4x, x8. So here out of order execution means add and sub is depend on add, right? No, so let me make it dependent. Now there is a data dependency here, right? So before maybe this data dependency can is solvable by data forwarding, right? But just assume that there is no data forwarding. So in that case there is a stall possible here, right? Or if I say that there is an instruction here, then also the और नहीं, इसको आइडियली बनाते हैं, एक लोड इंस्ट्रक्शन डाल देते हैं, लोड x1 एंड 4 सपोज 0x8. अभी तो पक्का से डिपेंडेंसी है, राइट? Because it is depend on x1, sub is x1 minus x4, but x1 is depend on load instruction, so there will be a stall here. So but this load instruction is independent, right? So out of order execution means every time you no need to follow pc plus 4. You can suppose here this first and second instructions are dependent, so they cannot proceed. So in that case the processor can start executing from the third instruction. That is called out of order execution. You can start executing out of order, but you will not commit in out of order. After execution, the results will be stored in a buffer, and commit will be in again program order. Okay, so if suppose let me go for one more example. If I write division here and I write x3, x5, x7, there is no data dependency, right? Division is an independent operation. So you can assume, suppose that there is a add functional unit, and there is a separate divisional functional unit for division in your processor. So suppose when there is a stall here, you cannot fetch, suppose because of some issue, because of structural hazard you cannot fetch sub. But see, you can fetch deep because this unit is free. So in that case you can fetch this third instruction out of order, and you can complete the execution, and result will be stored in a buffer. Result will be stored in a buffer, and commitment after executing the final result, the final write back will be in again program order. So that is called out of order execution. You no need to follow every time pc plus 4, because if you go out of order execution, it may be possible that you can utilize all the resources of processor much better in a much efficient way. The example I am giving here is this. Suppose there are two instruction, maybe the add instruction has structural hazard. You cannot issue another instruction because the add unit is busy. But you can see that down the line there may be the fourth or fifth instruction is a division instruction, and that division instruction you can perform because division unit is free, so you can fetch that instruction and you can perform the execution. But to do this, there should be some logic, right? And logic will be complex because the data path that we know is very simple. Every time we'll go pc plus 4, pc plus 4, very simple. But here since you want to go out of order execution, then the logic is complex. So that is called and for that we normally use two the well known algorithms are there. One is scoreboarding and one is Thomas Solo. You can know if you want to see more, you can just search scoreboarding, but these are very old. Scoreboarding, I think it's proposed in 1976. Tomasolo also, I think, before 1980. But they are well known algorithm used for out of order execution, and we normally don't discuss it in this computer architecture course, basic course, but at least you should know what is these two terms. And they normally used to schedule all this out of order execution. So if in this course, if you only know what is called out of order execution, then it is fine. But if you allow out of order execution, then there will be some more kind of hazards you will face. Till now, we know only three types of hazard, right? Structural hazard that we know if there are resource conflict, right? Structural hazard means if you have a arithmetic logic unit, so you cannot perform two addition at a time because you have only one resource there. So that is called structural hazard. Then we know about control hazard that is related with branch and all, right? So I'm not discussing this two, but third one is data hazard. So if I write a instruction like add x1 x2 x3, and here if I write one more add that x5 but x1 and x2, suppose x4, then there is a data dependency between these two, right? But uh, let me write one more line here, x1 read after write. So we normally call it read after write. Okay. So this data dependency you can resolve using data forwarding, right? But in out of order execution, it may create one more problem. Suppose this, if somehow this instruction executed before this, suppose this is 1 and this is 2. If the instruction number 2 executed somehow before instruction 1, then what value of x1 the second instruction will read? Old value, right? What value the second instruction should read? Updated value of x1. Only concentrate on x1. The second instruction should read the updated value of x1. And who is giving updated value? First instruction. But in out of order execution, if the instruction number 2 is executing before instruction 1, then it will create a problem, right? So this hazard is called read after write hazard. You have to read after write. It is called row hazard. So the data hazard that you know now will be divided into three parts. This is called read after write hazard. Now, one more point is add. This is another example. Add x1, x2, x3, and then add x2, x4, x5. Do you think there will be any issue here in second example? If we go the sequential execution that we know pre-midsem, there is no problem, right? There is no dependency. X1, X2, X3, second instruction is executing X4 and X5 and storing it at X2. So there should not be any issue. The concept that we know pre-meets them. But here in out of order execution, again there may be a issue. If I execute this instruction, second instruction fast, this is second, this is first instruction, then what value of x2 should read by this first instruction? It should be the old value, right? The value that is updating by x2 should not read by x1, the first instruction, isn't it? But here what will happen if you execute second instruction fast, then the value of x2 will be updated, and that updated value will read by the first instruction. That is again, that is a problem. So this is called write after read hazard. This is called write after read hazard. This type of hazard may also happen. Now the third type is add x1, x2, x3, add x1, x5, x6. There is two x1 here, and maybe assume that one more instruction is here, x7, x1, x8. There are two instruction add and add. Both are writing on X1, right? Both instruction, first and second instruction, are writing their result on register 1. And the third instruction is using register 1. So concentrate on third instruction. The third instruction, that X1, which value it should read? Update by first instruction or second instruction? Second instruction, right? But it somehow the first and two are reverse as per out of order execution. If the instruction number 2 execute first and instruction number 1 execute after the first instruction, then the sub will get the wrong value, right? Then the sub will get wrong value. This is called write after write hazard, wow hazard. So row, var, and wow, there are three types of data hazard if you go with out of order execution. But this situation is not there if we go with sequential execution. So try to understand one at a time. Row hazard, it's very straightforward. That we already know from pre-midsem, right? Row hazard, we know that the first write. If I'm saying about this one here, we should allow the first instruction to write before the second instruction should read. Otherwise, there will be a row hazard. Second is saying we should allow the first instruction to write before allowing the second instruction to read. Otherwise, the second instruction will read a wrong value here, isn't it? No, no, no. Right after read, we should allow the first instruction to read here before writing by second instruction. Otherwise, the value will be again wrong. This is called write after read hazard. Okay, and this is called write after write hazard. There are three types of hazard possible. So first hazard, that is a row, can be solved by data forwarding. It's not possible every time, but at least in some cases it is possible to resolve by data forwarding. One case when it is not possible to resolve by data forwarding is a load wala example I have given, right? But that is also a very idealistic example, and the data path that we assume is also very ideal. In real situation, execution stage may take more than one cycle. Means your addition will take suppose 2 cycle, then division will take 8 or 9 cycle, multiplication will take also like this. So it may happen that data forwarding is not a solution every time. Data forwarding is a solution here because every stage we assume that it is taking only one cycle, right? But if it is like this, that okay, addition is taking 3 cycles, execution stage only, addition is taking 3 cycle in execution stage, multiplication is taking 16 cycles, in that case there will be stalls, right? There will be stall. So to handle this, either you should go with out of order execution, or all these things are there. So in this course I don't want to make it complex, that's why I assume a very simple design. If you want to understand all the concepts that I'm saying now, then you can read the book of same author, but the book is called, I think, Computer Architecture, a Quantitative Approach. You can find this book in library, because we use that book as a textbook for advanced computer architecture. If you read that book, you'll find all the complex design, complex data path, that there are multiple functional unit, or multiple cycles are taking in addition, multiplication, and all. So but still, only technique to resolve row hazard is data forwarding. Can you resolve this hazard? Can you propose any technique? Don't think about architecture way. Suppose you are any in a simple way. If I rename this x2 as x2 dash, and because ultimately before executing this program in computer, that there will be assembly language code, right? First I will write a C program, then compiler will convert my code to assembly language code, right? So assume that ये row hazard वाला मैंने delete कर दिया. Suppose you have a long program, जो यहाँ पे भी बहुत सारे इंस्ट्रक्शंस है, यहाँ पे भी बहुत सारे इंस्ट्रक्शंस है, right? This is a program generated by compiler. After generating by compiler, assume that you have one more module is there in compiler, will check, oh, there is a word hazard here. So in this instance, so how compiler can resolve it? Compiler, one way is compiler can rename this register as x2, and then compiler will check after this instruction that which are the instruction using this x2. Suppose there is an instruction here called sub, it is like this x7 x8, x2, then it will rename this value also like x2 dash. If you do this type of register renaming, then the one other problem is resolved, right? If I can you are you understanding it now? There is do you think there will be any correctness issue? Previously the concentrated on second instruction was storing its result on x2, right? It is not using x2 or result खाली result store कर रहा था, right? So see, it is using x4 and x5 for addition, and it is only storing the result in x2. Now I'm saying no, I don't want to store result in x2, I'll store it in x2 dash. It's a different register. And in future I'll make sure that all the instruction who are using x2 now they will use x2 dash, so they are using the updated value. So and I'm only assumption is assume that there are infinite number of registers. Okay, so you can solve this problem by register renaming if you have enough number of registers, isn't it? Same problem you can solve here also in right after right. Can you can you verify it? I'm saying that in right after right also, if you can apply register renaming, then you can solve the problem.
Can we store the copy of original values in different registers? And if you want to use the original value, you can we can refer to that register. Otherwise, we can just refer to the this modified register.
If you want the original value, na, so suppose here, see, this is a sequential program, right? So if you modified x2 here, then every time obviously you need the updated value, right? There is no point that you should read the old value. I don't, it is not required here. This complicacy may come if you have a if statement, if you have a jump statement. I'm not making it complex, but if it's a sequential program like this, then every time you will read the old new value only, right? You no need to read the old value. So the same way here in the left side here, the right after right hazard, in this case also, if you make the second instruction here as x1 dash, and you make here also x1 dash, then I think you are resolving the right after right hazard. You no need to stall for it, right? So this thing here that I'm saying that possible to resolve by register renaming, the issue is in physical processors our registers are limited, right? You cannot use infinite number of variables. In program maybe it is possible, but here I am not discussing about, these are not variables, these are registers, and we have limited number of registers. So that's why the technique that is called Thomas Hollow, in Thomas Hollow they use a different technique, and in that technique you can use register renaming with limited number of registers, and that is called Thomas Hollow technique. So I'll not discuss that technique here because, but they use a concept called reorder buffer, and using that buffer, this their concept in such a way that yes, it's need to change something in processor also, but with a limited number of register you can implement register renaming. And if you can implement register renaming, then you are allowed to go out of order execution. And I hope you are understanding the benefit of out of order. If you go out of order, then you can improve the performance, because you can utilize the processor resources much in a much better way. But if you go to out of order, then these two are a challenge, right? War hazard and wow hazard, these two are challenge. So these two challenge can be resolved if you can perform a register renaming without depending on the number of registers. So that's why these two techniques can be handled. But you must understand that this type of hazards also occur, and these are very common. Even if you write any of these hazard like waw hazard, then you will find a page, and I think in gigs for gigs also. So it means that programmer should also know the concepts. Okay, so this is called instruction level parallelism. So whatever I have discussed in this slide are advanced concept, but that are for single processor, right? I never mentioned anything about multi-core here. So the processor that you have assumed in 1998 or 1999, that is Pentium 3, Pentium 4, in those processor also these techniques are there. It's not a new technique, because the algorithm that I'm saying, Thomas Solow, is proposed in 1970s. So the single core processor that we know from our 90s, those processor also use these techniques, and they use these techniques to improve the performance, to improve the speed of a single core processor, right? So suppose if you run a program on single core processor, and it is suppose it is taking 50 cycles, right? So after that, if you apply superscalar or if you apply autofetter, suppose your number of cycles now reduced to 50 from 90. Suppose initially it was 90, now it is 50. So in all the research in 90s were in this direction. So, and one more thing is increasing the frequency. One is increasing the frequency, then also you reduce the time. And how to improve the performance, like this called instruction level parallelism. If you parallel, somehow you can execute multiple instruction at a time, but all are depend on single core instructions. And it has been found by 2020 that no, you cannot proceed in this direction because of a major constraint that is called energy. If you keep on increasing frequency, then at certain level it is not possible to maintain that temperature, and the chip will burn. So at that point, I think in initial of this 2020, people were thinking that no more advancement possible in computer architecture, because we have reached the extreme limit and we cannot increase the frequency anymore. And from that point, the concept of multiprocessor came, right? So in multiprocessor, normally we have multiple core. I think this type of small basic design I have used many time already in this class. So suppose there are 4 core. All the core has their common private L1 cache. I have used it for cache coherence also, right? So I think you are knowing it. And they are sharing a last level cache as L2. So in multiprocessor, maybe the frequency is less, but you can run 4 works simultaneously, right? P1, P2, P3, and P4. 4 works you can run simultaneously. So maybe one task is taking the same amount of time, but now you have 4 different tasks, and 4 different tasks you can simultaneously perform in a single computer. So that is the main benefit of multiprocessor. And in the two terms that I'm using here, task level parallelism and program level parallelism, these two terms are taken from book. Task level parallelism means this concept that I'm explaining is called task level parallelism, or program level parallelism means 2 program, or here you can run parallel, or 4 program you can run in parallel, or you can also say them as task. So 4 tasks you can run in parallel if you have a 4 core multiprocessor, right? In this multiprocessor there are 4 cores. But what about if you have a single core, a single program, but very complex program? You don't have 4 program, you have only one program, that is P1. It's a very complex program. Suppose it's a program related with big data, or suppose it's a program based on some machine learning techniques or something. So it's a very huge program, but you have a single program and you have multi-core processor. So how to improve the performance? If you simply write a program like the way we write in our C G103 matrix multiplication type of program, it is a sequential program, right? आपके पास 8 core हो या 16 core हो, it will only use 1 core and it will not improve the performance. So this is the challenge, parallel processing program. And this chapter 6 is mainly based on initially the discussion what are the issues that the software engineer face to make your program utilize the number of cores. Otherwise, suppose you are my I have two team. One team is designing the software and another team is a very small team. They are only involved on purchasing processor, but I have enough money. So if I decide no, I have enough money, so let us move to a 16 core processor. So I purchase all the 16 core processor, but my software team has no idea how to extend this program P1 for 16 core. So that program will again run on a single core, right? So that's why this is a challenge, and in that challenge, even it is now a responsibility of software engineer also to understand the behavior of a architecture, and to design a program in such a way that if it's run on a 4 core machine, it should utilize all the 4 core. If it is run on a 16 core machine, it should utilize all the 16 cores. So I hope you are understanding that challenge is also on software engineers. It's not like that you will write a sequential code and it will give better performance. Though in modern day there are some tool exist which can convert your sequential code to this type of code, but still, but that even those tool will also designed by some people, right? And you may be one of them because you are an engineer. You are not a BCA or MCA student, right? So you should understand all the concept. And shared memory processor means this multi-core processor is called shared memory processor. Normally we call it SMP. Some of the points that I'm discussing maybe they are not directly connected, but today I'm only explaining some each term separately, because in next lecture, when I'll start chapter 6, you will see all the terms, and I'm just trying to clear all the terms here. Maybe you will not find much connection what I am discussing today. Shared memory processor means the memory that I'm showing here, this multi-core, this is called shared memory because they assume only one physical memory. Physical memory means RAM. Okay, physical memory, because I explained you, right, what is called virtual memory, what is called physical memory. So maybe there are four cores here, and four code can execute four different processor, p1, p2, p4, p1, p2, p3, p4. Each process has its own virtual memory, that is fine, but physical memory is same, isn't it? If there is a multi-core processor, the physical memory is same, that is RAM. So all the multiprocessor that we normally discussed here in this course so far, I have discussed different replacement policies, and I say that the replacement policies are executed on single core as well as on multi-core, multiple core, and then they show the results, right? All are actually this SMP. They are actually shared memory processor. But maybe you have heard a term called cloud, right? So in cloud, what is happening? It's cloud means there are multiple computers, right? Multiple small computers connected through some network. So in that case, maybe each computer has this separate physical address also. So that normally called as cluster. If you see this book, the term they use for is called cluster. Cluster means there may be multiple small computers. So each computer has its own RAM. So in that case, you can say that no, they are not sharing the physical address. So they are not SMP. So cloud is not like the actual cloud. I hope you understand. And right, every time we say that data is saved in cloud, ultimately data is saved in a server only, but its server is a small connection of small computers connected with the network. So that is called cloud. Okay, so is there any other slides? Yeah. So the last slide is Amdahl's law. So just remember this term. This term it will be used in next lecture. So multiprocessor I will explain, task level parallelism, program level parallelism I will explain. But challenge here is parallel processing program. And this challenge we will discuss in the chapter mainly discuss this challenge, that how to design a program like this P1, which can get benefit from a multi-core processor. That's why it is called parallel execution or parallel processing. Amdahl's law, it is mentioned in chapter 1 only, but at that time I skipped it. Amdahl's law. So Amdahl's law means if you have a computer, suppose this is a computer, and here if you run a program P1 and it is taking suppose 15 nanosecond to complete, and it has different functional units. Suppose there is a functional unit called for add, there is a functional unit for multiplication, and suppose add is taking 2 cycles, multiplication unit is taking 15 cycles, suppose. But assume that there are some research happened, and based on this research, this multiplication unit is now improved. Somehow it is improved, and now instead of 15 it is just taking 10 cycles, but addition is still taking 2 cycles. So it means that you have not improved the entire computer, you have improved a fraction of this computer, right? So if you improve a fraction of this computer, then what will be the speed up? So that is given by Amdahl's law. Okay, so originally it was there was a machine, right? There was a computer. So the speed up will be execution time before and execution time after, or you can say execution time before modification divided by execution time after modification. So that there can be different type of modification. This is the example that I've given, that we have improved the multiplication module. This is just an example, it can be anything. So the speed up here, according to Amdahl's law, is execution time before modification, or you can say before improvement, divided by execution time after an improvement. So if you go to the next diagram here, this is it's a screenshot taken from your textbook. So what about execution time after improvement? So execution time after an improvement, you can calculate with this formula. Execution time affected by improvement. So you can see here, this part is not affected by improvement, right? Addition part is not affected by improvement, only this part is affected by improvement. So here it is saying that execution time affected by improvement divided by the amount of improvement plus execution time unaffected. So if this thing is giving you execution time after improvement, okay, this same concept you can write in this format. So see, execution time unaffected can be written as like this: execution time before minus execution time affected. So execution time before modification minus execution time after execution time affected will give you execution time unaffected. So these two are same thing. So here instead of writing this, I can also write execution time unaffected, not division. I can, instead of this, I can also write this. I can also write this. This called speed up. It is starting with same. It's very simple. Execution time before improvement, execution time after improvement, and then here in this diagram, we are trying to. This is actually the Amdahl's law. What is execution time after improvement? Execution time after improvement is execution time affected by improvement divided by amount of improvement plus execution time unaffected. Okay, so in actually if you go to Wikipedia, then you'll find a formula like this: speed up here s equal to, I think, 1 by 1 minus p plus p by something a, or you'll find a formula. This is called Amdahl's law. Here execution time they assume as 1, execution time before is assume 1, and here this is execution time affected is p, so 1 minus p, and this is execution time affected plus this is the amount of improvement. So this formula you'll find. How much time I have? I have a example. uh, so suppose there is a example here. You can watch this lecture and you can ask your doubt tomorrow. Suppose I have there is a computer where I need to perform a addition of this much. There are, suppose, x1 to x10. There are 10 values are there. So I need to perform addition of this 10 value, and then I have two matrix here. These are 10 cross 10 matrix. I need to perform the addition. So what should be the result? After this, here will be a result R, x1 plus x2 plus x3 plus x10. And from here, I have one more 10 cross 10 matrix, right? So I want to perform these two operation. Oh, I think there is a class here. So I'll stop here. I'll continue from this point again. I'll explain you Amdahl's law, and then I'll start chapter 6 in next lecture.